Hello and welcome to the 2021 Quantum Summer Camp's virtual poster session. We are excited and delighted to share the research we have done this summer with you. So now, we will begin our discussion with an introduction to one of the most fascinating physical theories, quantum mechanics. Quantum mechanics is the study of atoms and subatomic particles. It is a fast-growing field in physics. Not only do quantum effects directly defy our everyday life or classical understandings of reality, the effects being discovered could have profound implications for computing and communications. Since time immemorial, the nature of light has been a mystery. Isaac Newton proposed the view that light is made up of particles, but it was later discovered that light also behaves like a wave. The world we accepted today is that it behaves like neither, sometimes behaving like a particle and sometimes like a wave. The best way to investigate this nature is by performing the double-slit experiment. This visualization of the double-slit experiment shows that when classical particles are sent through two slits, they form two piles, one behind each slit. Think of what would happen if you poured grains of sand through a piece of wood with two slits. When waves are sent through the slits instead, they interfere, resulting in a fringe pattern called the interference pattern on a screen. When the crests and troughs of a wave meet, they cancel each other and give us a dark fringe, which we call destructive interference. When crests and crests or troughs and troughs meet, they add up and give us the bright fringes we see here. And we call this constructive interference, and this results in the interference pattern we see here. When we send a quantum object, called quanton, through the double-slit experiment, classically we would expect it to act like a tiny particle and form two bright stripes behind each of the slits. However, when we send a quanton, like a photon or electron, through the experiment, we find an interference pattern, just like we get with waves. This happens even if only one quanton is in the experiment at a time. Somehow, the quanton is interfering with itself. But this behavior changes when we introduce an observer into the experiment. The result is that no interference pattern is observed, just like in the case of classical particles. When we send a quantum object through the two slits, it exhibits a phenomenon that we physicists like to call superposition. It is when a quanton, unlike particles, has multiple ways of passing through the two slits. Superposition is the ability of a quantum system to be in multiple states at the same time until measured. According to classical thinking, a single quanton has four possibilities. Enter slit 1, enter slit 2, enter both slits, or enter neither slits. However, none of these match with experimental observations. If a quanton is measured going through slit 1 or slit 2, the interference disappears. If the quanton goes through neither slit, it won't reach the screen behind. We never measure half a quanton, so it can't be going through both. The resulting none of the above option is called superposition. Once it reaches the screen, it assumes one position on the screen like a particle, but it also exhibits an interference pattern like a wave, which is another quantum behavior we mentioned earlier called wave-particle duality. The act of observing or making a measurement destroys the interference pattern, and this shows the bizarre nature of light and quantum mechanics. The strangeness of quantum entities does not end here. Another phenomenon that has baffled many scientists, including Albert Einstein, is entanglement. Entanglement is a phenomenon that occurs when measurement of one of a pair of particles, such as photons, determines the outcome of the measurement of the other particle regardless of the distance between them. In order to comprehend the nature of one of the particles, one has to relate it to the nature of the other. The individual particles actually exist in all possible states, but when measured or observed, it displays only one state. In addition to that, when the nature of one of the particles is measured, it instantaneously affects the nature of the other. This is the reason Einstein referred to this nature as a spooky action at a distance. Thus, entanglement is the nature of the two particles being connected to each other and actions executed on one affect the other. Let's take a look at a classical example. Imagine you and a friend seal a pair of gloves into two boxes and each take one. When you look at your box and find that you have the left glove, you immediately know that your friend has the right glove. This is a similar idea to quantum entanglement, except that in the quantum world, neither glove has a defined left or rightness until you look in your box. Once you look, your glove assumes a defined state, left, and the state of your friend's glove immediately becomes right. One final quantum principle to understand is the Heisenberg uncertainty principle. According to this principle, there are certain pairs of qualities that are incompatible observables. If you measure one, you can't measure the other. If you know one with a low uncertainty, you know the other with a high uncertainty. A common example is position and momentum, but other examples exist as well. For our experiment, it's important to know that energy and time are incompatible observables. In order to understand and further investigate these quantum behaviors and other bizarre behaviors which we will introduce in a series of videos, we decided to perform a single photon interference experiment which demonstrates these quantum effects. It's similar to the double slit experiment, although simplified through the use of a device called the interferometer.